Welcome back. In this and the next few lectures, we're going to look at symbol tables, a fundamental and extremely important data type that have led to all kinds of fascinating implementations, and we're going to look at several of them in this course. To begin, we'll take a look at the API and some elementary implementations and various operations that people want to perform on symbol tables. Start with the API. The idea behind symbol tables is to implement the following abstraction. We're going to have keys, like our keys in priority queues, but the whole idea is that we're going to want to associate values with each key. So the two operations that we're going to perform in symbol tables is the insert operation, where we're really putting a key value pair into the symbol table, a value with a specified key. And then given a key, we want to search for the corresponding value. Those are the two basic operations. Now the keys and the values can interchange roles, and that's why we have the abstraction to separate them. So for example, a domain name server might have a lookup where you've got a table that's got an IP address and a URL associated with that IP address. And different clients might want to use this data in different ways. One might want to use the URL as key. Given the URL, give us the corresponding IP address. Another client might want to use the IP address as key, have an IP address, give me the corresponding client. So those are just a couple of examples. This is a very fundamental and basic abstraction. And the list of applications is huge. In fact, almost any computer application system is going to have a symbol table or multiple symbol tables at its core. All the way down to the basic memory system of the computer or the networking system that your computer access to information depends on. You can think of it intuitively as like a dictionary. Well, there used to be books, and people would open up those books to look for a word to find the definition. Nowadays, you're more likely to do that online. Or when you're trying to find a song to download, you provide the name of the song, and then the value will tell you what computer to go to get that. Or in commercial computing, the key might be an account number, and the value might be the transaction details for that account. Web search is something we all do multiple times every day, and the key is a keyword or a list of keywords, and the value is a list of places where that keyword is found. And there's many, many other applications, including scientific applications, where, say in genomics, people use symbol tables to keep track of finding markers in a genome, and again, many other applications. So it's a very fundamental concept, and we'll look at plenty of applications, but first we want to look at some algorithms. So the way that it's convenient to set up a symbol table is to implement the so-called associative array abstraction. And the idea behind that is to think about just associating one value with each key. Well, it's like in a Java array of integers, say. Our keys in that case are indices that are restricted to be between 0 and the array size, but we're only associating one value with each index. We think of storing the value in the array position given by that index. And a good way to think of a symbol table is as shown in the right here. When we put a key value pair onto the symbol table, think of that as using the key to index an array and storing the value there. Now this isn't legal in Java if key is not an int, and we're going to do this generic. It can be any type of data. But it's a good way to think about it. And then to retrieve it, you just give that same key and it'll return the value. So that's our two primary operations. Put a key value pair into the table, so that is associate the value with key, and then get the value paired with the key. There's particular rules for null that I'll talk about in a second. And then to properly maintain a symbol table in a dynamic situation, in many clients you want to support a delete operation, and contains is a simpler operation than get. It's convenient for many clients, where it just tells us whether there's some value paired with that key in the table, is empty in size. And then another thing that you might want to do is iterate through all the keys in the table. So those are the basic operations that we're going to want to implement to get the associative array abstraction. And then there's many, many possibilities for clients, and we'll look at some later on. Now there's a couple of conventions around null. And these are not critical, but they make it a bit more convenient to, for several implementations. So we're not going to allow null values. You can't associate null with any key. And then we're going to adopt the convention that the get method returns null if the key is not present in the table. And also the associative array abstraction is the put method will overwrite an old value with a new value. So these are our consequences. So it's the contains implementation is the same for all our symbol table implementations. If get returns a non-null value, then there's a value corresponding to that key in the table. If it returns null, it's not. Get returns null if key is not present. And the other thing that we can do is we can use null in some situations or temporary situations to implement a lazy version of the delete operation. We can associate the key with null internally, and then the client won't know the difference whether that's in there or not. And some algorithms take advantage of the ability to use null in this way. These are just conventions and somewhat details, but it's important to point them out at front. So now we're going to want the value to be any generic type at all, but the key type we have to make some natural assumptions about them. And actually there's different assumptions that we make in our implementations depending on the application. One of the most useful ones is to have comparable keys. Just as in sorting algorithms, we'll assume that the keys have are values that come from a total order, and we can use compare to compare whether one key is less than another or not. This is for two reasons. One is we can get more efficient implementations if we can use the ordering of the keys to help us find our way around the data structure. And the other reason is that we can support a broader set of symbol table operations that are very convenient for many clients. And it's very typical for keys to come from an ordered set, for example, in the dictionary application, or if keys are strings or numbers or count numbers or many other situations. So if they're going to be comparable, we might as well take advantage of it, both to get more efficient algorithms and to be able to take advantage of a broader set of operations. Now in other situations, maybe they're not comparable, and all we are allowed to use is to use the equals operation. That is, everything, every type of data in Java has to support an equals operation. That we use that to test whether they're equal. And there's another family of methods where there's no ordering, and there's a special method called hash code that helps us inject randomness into the process. That's built into Java, and also some classic algorithms depend on that. We're going to start out with the comparable mostly. And again, as with priority queues, the best practice is to use immutable types. And experienced programmers know this, and it's not difficult to arrange for the natural types of data that people are going to use for symbol table keys. Unreasonable to expect the implementation to work well if the client can change the values of keys that are in the table. If you want that, you have to provide that as a specific operation. But in case of symbol tables, we're not going to do that. You'd have to remove it and put it back in. All right, so there's equalities. Now equality, again, we're getting into a programming language issue, but still it's important to be explicit about what's going on with equality. How do we test if two objects are equal? Java's got requirements as for compare to, and here's the basic requirements about equals. There's a method that all Java classes inherit for equals, but the default implementation is simply to test whether the references are equal. Are those precisely the same objects or not? Usually in applications, when we want to have something more general than that, have a concept of a value, or like a key in our case, and then we want to know if two references refer to objects that have the same value, and we want to call that equal. That's what equals is about. So anyway, we're required to make sure that x is always equal to x, and that x equals y is the same as y equals x. And if x equals y, y equals z, then x equals z. So that means that in mathematical terms, equals is called an equivalence relation. And also, no object is equal to null. So those are absolute requirements for Java. And again, the default implementation is to check whether they refer to the same object, and that's rarely what we want. Java systems programs maybe want that, but client programs usually have customized implementations that are based on comparing some sort of value. And the standard built-in types of the Java language are going to have those customized implementations, and we can rely on them doing what we expect. If we're going to implement our own types and then use those types as keys in symbol tables, you have to exercise a little bit of care, and we'll talk about that briefly. So say we have this simplified date implementation that we had talked about before. It's a mutable type, and every date's got a month, a day, and a year. It seems like it should be easy to implement equals. Basically, we're just going to check that all the significant fields are the same. Two dates should be equal if they have the same day, month, and year, and if any one of those are not the same value, then just return false. So that seems as if it should work, but that doesn't have all the characteristics that we need in a Java implementation. And so all of this code in red shows a model for what you might do if you're going to implement your own type of data, equals for your own type of data. Shouldn't use it in connection with inheritance, so we don't use inheritance that much, so I won't talk about that. The type of the argument in the equals must be object. You'd think it should be date, and experts debate about that, and people who are interested can look on the web for that kind of date. If it is the case that you happen to be testing two objects that are the same object for equality, you might as well optimize everything and just test that. If y is a reference that's pointing to the same object as this object, just return true, because if you're going to test the values, they're going to have the same values anyway. And that's a good optimization for lots of situations. Why go through all that rest of that code if you know right away they're equal? There's this test for null that has to be there, and if it's not there, can lead to nefarious bugs and unusual problems. So your equals test, you better test that the client didn't give you null. They have to be in the same class, and well, there's a couple of different ways to check about the same class, and that's another religious debate that we'll ignore. We'll use get class, and that's something that's got to work, or they'll get an exception in this later code, because since y had to be an object, now we have to cast it to a date. And then it better be the right class, or otherwise it's not going to have these fields that we can test for. Details, but anyway, you can use this code as a model to implement equals for any data type that you might wind up using as a symbol table key. Okay, so that's a standard, this is just in words, the standard recipe for user-defined type, optimized for reference equality, check against null, make sure they're the same type and do the casting, and then compare all the similar and significant fields. It could be that if one of the fields is an object, then you use that object's equals, which applies the rule recursively. And then if you have a field that's an array, you can go ahead and try applying it to each entry. And there's implementations in Java. You don't want to use a.equals b. That checks if those arrays are the same objects, and that's not what you want. You want to check that all the values are the same. And if it's an array of objects, you can see that testing for equals can actually involve a lot of code and a lot of cost. All right, so, and certainly you want to follow some of these best practices. So fields that are most likely to differ, those are the ones you might want to compare first. And you're also going to want to make compare to consistent with equals. Though we'll generally, if we have comparable types, we'll use compare to, and if we don't have comparable types, we'll use equals. Okay, so now let's look at a couple of test clients before we look at any particular implementation. So this is a test client. So symbol tables are, ST is the type, symbol table. They're generic on key and value. And so this statement builds a new symbol table with string keys and integer values. So it's going to associate integers with strings. And so what the test client's going to do is going to just go in a loop as long as standard in is not empty, and it's going to read strings, read a string off standard input, and then put it in the symbol table associated with the value I, where did it appear in the input. So this is an indexing client where we associate each string with its position, most recent position in the input. And notice it's an associative array implementation. So for example, we have two E's, and at the end, E is associated with value 12, the place where it most recently appeared. We could also keep these things in a bag and do a client that gives all the positions that appeared. This is a simple indexing client that we use for our traces. For analysis, for bigger problems, we'll use a client called a frequency counter client. And so that one is going to read a sequence of strings from standard input and print out the one that occurs with highest frequency. So for this small data from the beginning of Dickens' Tale of Two Cities, if we run a frequency counter, the frequency counter client, and this first argument is just ignore words of fewer than this many letters. It'll say that the most frequent word, where there's no word that appears more frequently than it, which appears 10 times. And we'll want this client to work well for huge data sets. So Leipzig is a data set from the web of 20 million words, about 500,000 distinct ones. And in that corpus, the word government appears about 25,000 times. So if you have a quadratic time algorithm for implementing symbol tables or linear time for each operation, you're not going to be able to run this client in a reasonable amount of time for a big amount of data. So that's the client that we're going to use for analysis. Here's the code for that frequency counter client. Again, it's similar to the other one. We're creating a symbol table that associates strings with integers. We take that command line argument, which is the minimum length that we care about. We'll read a new word. and we'll ignore the short strings, just trap out if the word length is too small. And now the integer that we're going to associate with each word is the frequency of occurrence of that word in the symbol table. So if the word's not in the symbol table, we'll put it there with a frequency of occurrence of 1. That's the first time we saw the word. If it is in the symbol table, we'll just overwrite the old value, which is stgetWord, with the new value, stgetWord plus 1. So increment the frequency in the symbol table. So this loop reads in all the data and associates each word with its frequency of occurrence. And then we'll have a client that uses the iterator going through all the keys in the symbol table. It'll get the value associated with each key. And if that's bigger than the maximum found so far, we'll save that away and then print out the word that occurs the most often along with its frequency. So this is a useful and non-trivial client that's enabled by symbol table. But it won't work well unless we have an efficient symbol table operation. And we'll use this client to compare different symbol table implementations. So that's the symbol table API, and next we'll take a look at implementations.